Hello, friends. This is an introduction to Schrodinger's equation. Let's do it. All right. Figuring out the whiteboard. So, Schrodinger's equation. Already check this out. This is pretty cool. Oh. And what I'm also going to do is outline precise, exact solutions that you should know. So how does this work? So we have the most important equation in physics, we realize now, is conservation of energy. That potential energy plus kinetic energy equals E total. And it's really important to know that this is a constant. And so a question is going to be, what is it? And classically, we're going to look at some examples. You would say, okay, E total is the initial, naught is initial, plus KE initial, or final plus KE final, whatever. So you're going to get it from that information. So it depends on the information you have. What we're going to see is that it's probably going to come from a different source. It's going to come from Schrodinger's equation in the quantum way. Although we've already done this for dropping a particle, for example. Anyway, so classically, this is how it's typically done. Remember that the potential energy, by the way, all of this is important, right? Understanding this, so please pause if it doesn't make sense. This comes from forces in the scenario. It doesn't come from forces. I should say, it describes the forces of the scenario. So let's actually say that. Erase. It describes the forces of the scenario. It's precise forces in scenario. So the whole point is we're going to look at it this way. So remembering that force is the negative slope of potential energy. And that's really important. So we're going to do it this order of operations. That psi of x, right, gives you kinetic energy, which gives you the potential energy, which tells you the force, which means this is your physical situation. This is what's actually happening. But the forces also determine the potential energy, which determines the kinetic energy, which determines this, which is like the probability of finding a particle. Classically, what you would do, right, classical, you use this to solve for the velocity, right? You would say classically, oh, okay, 1/2 mv squared is kinetic energy. So if I know the potential energy, I know the kinetic energy. And if I know the kinetic energy, I know the velocity at any moment. So we can always look at the classical analog for any of these, and we're going to want to do that. Just to compare, like completely different worldviews. Anyway, here's what we're doing. So this is actually Schrodinger's equation. Dun, dun, dun. I was like, how do I reveal this? It's like, we already know it. This is Schrodinger's equation. This is it. Essentially, we need to like tweak it a little bit to adapt it to quantum mechanics, and we already know how to do that. We secretly already have done this. And I did reveal to you that what Schrodinger figured out, although they were all working together at the time, all of these physicists, is that, so kinetic energy is negative h bar squared over 2m times the curvature of psi divided by psi. So what you do is you plug this in to this. And the whole point is plugging this in to here turns this into the true form of Schrodinger equation, Schrodinger's equation. But this is Schrodinger's equation with this plugged in, because this is now kinetic energy. So instead of 1/2 mv squared, which is the classical version of this, we have this, the quantum kinetic energy is that. So that's it. So here we go. So we have, and sometimes curvature is written as the second derivative, which is d dx squared. If that makes no sense to you, don't worry about it, but you'll notice that if you have done derivatives, that's the second derivative in derivative notation. So I'm going to write this in 3 separate ways. The first way is that potential energy, minus h bar squared over 2m times the curvature of psi all over psi equals E total. That's Schrodinger's equation number 1. Schrodinger's equation number 2 is where we multiply by psi, and we could write this as the second derivative. And so I say, okay, potential energy times psi. I multiply every term times psi. So this times psi, this times psi, and this times psi. I get potential energy times psi. Psi here cancels, and I get minus h bar squared over 2m times d squared dx squared of psi, which is the second derivative. This is the curvature, equals E total times psi. Another way this is written is you will sometimes subtract this over and add this over. So you get potential energy minus E total times psi equals h bar squared over 2m, because that way you get rid of this minus sign and you isolate the terms that are connected to psi like this and you factor them out, times the curvature, which I'm going to write as the second derivative. By the way, I want to be perfectly clear right now. Please listen to this. I'm not going to ask anybody to do second derivatives. You don't have to do calculus to do this class. Please, if you're like, oh, I don't know second derivative, don't freak out. You're not going to have to learn it. I'm going to give this to you, right? I will give this to you. But if you are in calculus, I will have a bonus saying, well, you can do the second derivative yourself. Have fun. You can then take that next step, but I will give this to you. You're like, okay, cool. So I'm just going to give that to you, and then you can plug it into the equation, and notice you can solve for psi. Isn't that cool? Or typically, what we're going to do is solve for E total or solve for potential energy. How we write this equation will depend on what we want to solve for, but these are the forms that it's going to take. Typically, this first one right here. Typically, this one and this one, but also these. So here's how we do this. So like I said, we can start with psi, or we can start with potential energy. I'm going to start with psi. Let's start with this. And let's freeze time. Just say time equals 0. So that becomes just a sine wave. So if this is just a sine wave, what is E total? And what is potential energy? And we're going to figure out the order in which we do this. This is going to be typically how we do it. We start with a sine wave and say, is this a physical situation? Right? That's kind of like the side question. It's like, is this a real physical situation or realistic wave function? I don't know. Well, we know that it's a free particle, but let's say we didn't know that. So let's plug this in to Schrodinger's equation and see what we get. So here's what we get. So we get potential energy, right, minus h bar squared over 2m. I'm going to plug it into this one. Again, I'm typically doing this one, right? So minus h bar squared over 2m times the curvature of psi. So here's where the curvature comes in. Again, I will give it to you, and here's where something interesting comes in. So I'm going to slow down a little bit. That the second derivative of psi, if this is psi, otherwise known as psi double prime. If you've taken calculus, you know that. Either way, this is what it is. It is negative. This is called the chain rule. This gets pulled out twice, one for each derivative, and the derivative of sine is cosine. The slope of sine is cosine. The second, the curvature, therefore, is negative sine. So you get negative a k squared sine of kx. So notice how it's the same thing, but with a negative sign and a k squared. That's a big deal. So we have h bar squared over 2m times negative a k squared sine of kx. So if that didn't make sense, just trust, okay, this is the curvature of a sine of kx. It just is. Now, if you want to graph this and show that when this is big, the curvature is big. When this is zero, the curvature is zero. On this function, you can play in Desmos and convince yourself that this is the curvature of this, that the concavity matches, the severity of the curvature matches. It's cool, right? So the curvature of this is this, right? So this equals E total straight up. Oh, we need to divide by psi, but actually, yeah, I'm going to divide by psi. And I realize I've cluttered my drawing. So let me erase. And I'm going to, remember, we need to divide by psi. In Schrodinger's equation, we need to divide by psi. Please don't forget that. So I'm just literally plugging this into the equation very slowly. A sine kx. Right? Because remember, it's potential energy minus h bar squared over 2m times curve of psi, which I've given to you. This is the curvature of psi, right? Over psi, don't forget to divide by psi, equals E total. This is Schrodinger's equation. Conservation of energy. Potential energy, here's kinetic energy, here's E total. Now, how is this kinetic energy? Again, this is a mathematical model that works. Trust the math. And be meticulous. We're going to go slow through these questions, and we're just going to do a bunch, right? So curvature of psi, great. So notice that the a's cancel, the sine kx cancels, and I get negative, negative, so I get potential energy. So then this transforms into, and this will be the next line down, but I'm doing it over here. Potential energy times negative, negative gives me positive h bar squared k squared over 2m equals E total, which means h bar squared k squared over 2m equals E total minus potential energy. Now, these are all positive. So this is kind of like our answer. Now we need to interpret it. So I'm going to rewrite this on the next screen, right? So we have sometimes an answer that might not be obvious as an answer, but here's our answer. H bar squared k squared over 2m equals E total minus PE. These are all positive. So E total is greater than PE. And remember, potential energy plus kinetic energy equals E total. Really important point here. That means kinetic energy equals E total minus potential energy. This is kinetic energy of X if you were to graph it. And sometimes we're going to do this. This is really important. But conceptually, this means that if potential energy is less than E total, kinetic energy is positive. So all positive. So we have a kinetic energy is positive situation. So we have a wavy wave, which of course we do. It's confirming that we have a wavy wave, but we already knew that because this came from this. So we're just confirming this is all positive. That we can now introduce this in general, that we have, so this is true. And then in general, conceptually, if potential energy, though, is greater than E total, meaning the object does not have enough energy to overcome the potential energy, then kinetic energy is negative. And I'll put an exclamation point for both of those. Right? Kinetic energy here is greater than zero. Here, kinetic energy is less than zero in general. So in this specific situation, we have all positive, so therefore E total is greater than PE. So we also can solve for K. And here's the whole point, right? So this, right, is kinetic energy, right? But remember, momentum equals h bar k, right? So the whole point is that this, if I plug that in here, is p squared over 2m equals kinetic energy. So we get that reproduced. Great. But I think more importantly, what we get from this, so we're just reproducing the equations that we already know, right? If we do h bar squared, k squared over 2m equals E total minus potential energy. I said, what is potential energy? What is E total? But all of these are constants. And this is a constant. So therefore, this is a constant. So PE is a constant and less than E total. All right. So specifically, how we could say it is E total equals h bar squared k squared over 2m minus, sorry, plus potential energy. This is just rewriting the equation again. Or we can say potential energy is E total minus h bar squared k squared over 2m. So you might say, how do we know E total and potential energy? But the answer is we don't. We can only write them in terms of each other. I didn't know I could scroll. And now I'm lost. Okay, that was cool. We can only know them in terms of each other. Like that. But we know this is true. So from this, we get this. So this is a constant potential energy situation. And remember, a constant potential energy situation, if I were to graph it, so this is like what we do, right? I graph a constant potential energy. The slope of potential energy is zero, which means the force, which is the negative slope of potential energy, is also zero. So that means this is a force equals zero situation, which means a free particle. So this analysis of this is constant, therefore, and this is constant by definition, and therefore this is constant. And if we wanted to solve for one or the other, we would have to know some other information. This is a very general thing. And really, we can also solve for K, which is kind of fun. K equals, sometimes it's E total minus PE is put together. I have 2m E total minus PE over h bar, and then the square root of both sides gives me that. And the h bar squared just square roots to h bar. So this ends up being a sine this. X. All right, minus omega t. And I can get omega from this because I can set omega equal to h bar times kinetic energy, and I can go from there. But just showing you I can plug this back into the equation to be a little more accurate in defining k, the wave number, in terms of the energies. But the main, that was sort of somewhat an aside. This is an aside. This is the main point here. That if I have potential energy less than E total, which means I have enough energy to overcome PE, which also means that kinetic energy is positive. Great. This is the situation I have. Notice this all came from what? This all came from, I want to know what is the situation for this? What is the situation for this? What is E total and what is PE? And then, of course, what is the force? And what we get, and I hope this makes sense, don't want to overthink it, we got that PE is constant, which means force is 0. Now, constant what? Remember, it doesn't matter. So I can arbitrarily set it to 0. Remember, we can still apply those classical rules. Quantum doesn't override that. Quantum still says you can set potential energy to anything you want as long as it's less than E total. You're going to get this situation. That's it. Don't overthink it. Got it. New Zoom rules. Buttons. I went slow for that one. I hope that made sense. Next video, I'm going to do the exact same thing, but for tunneling. See you soon.